Good. Yeah, it works.
Yeah. Okay, so let us start today's session, and I'm happy to welcome Ning Su from PISA. So Ning is an expert in conformal bootstrap, in particular numerical conformal bootstrap, and he has been behind some of these recent developments that David Pollan told us about yesterday. In particular, he was one of the people behind the cutting surface algorithm. And today he's going to tell us about some of his recent work on the Navigator function. Please, Ning.
Thanks for the introduction, and thanks for giving me this opportunity to talk about our recent work. This talk is based on the work with Martin, Slava, David, Benoit, and Belt. In this talk, I want to discuss a cutting-edge numerical technique, which, in my opinion, can largely replace the traditional method and do many more things. So in first part of my talk, I will discuss the traditional numerical method and some difficulties that traditional method cannot handle efficiently. Then I will present our method and also some technical details. Yesterday, David Poland showed us this nice 3D icing island, as well as the Super-Ising 0203 Grosvenor Island. In my talk, I want to show you in practice how can we plot an island like this. So let me quickly review the feasibility test. From Alexandra's note, we know if this is our bootstrap equation, we want to use it. We want to find a linear function of alpha, such that alpha acting on the convolved conformal block is positive. So if we draw those f delta L, so first we have to, we can use derivative basis to expand the linear function. And if we draw those block in derivative basis, those are the arrows in this plot. And find an alpha such that this condition is satisfied. Geometrically, that means we want to find a plane such that all the vectors are on one side of the plane. If we can find such alpha, then it's impossible for us to sum up those vectors with positive coefficient and get 0. So if we find such alpha, that means our assumption on delta L is excluded. On the other hand, if we cannot find such alpha, that means it's possible to make the equation hold. Such problem can be effectively solved using SDPB package. So in order to get the bootstrap island, in practice, what we do is that usually we have some estimation of the critical exponent from either epsilon expansion or Monte Carlo simulation. So we usually start with some small number and run do feasibility test for a few points in the parameter space that near our estimation of the critical points. If we are unlucky, if we cannot find any feasible point, we either test more points, or we have to decrease lambda, or we have to improve our estimation on the critical exponents. If we are lucky, if we can find a feasible point, then we can scan the island and gradually increase lambda and repeat this process. So let's take an Ising model as an example. From epsilon expansion, we know delta sigma is around 0.518, and delta epsilon is around 1.412. So first we choose a small lambda 19, and we do feasibility test around this region, and we can find a feasible point. Then we scan this whole island. Then inside the island, we increase lambda and do more tests. Then we might be able to hit lambda 27 island, then scan the lambda 27 island and gradually increase lambda. So in the bootstrap literature, you often see a series of islands labeled by lambda. The reason is not because we love those islands at different lambda, but the reason is that if we directly start with lambda equals to 43, then the island might be too small, so that we might miss it. We might not be able to find it. So we say there is a dilemma. The dilemma is that on one hand, we want the bootstrap constraint to be strong. So the island is small and the precision is good. But on the other hand, if the constraint is really strong, we might not be able to find the island. So in the past, to handle this, our strategy is always that we start from something known and gradually increase lambda. This is bad because one reason is that it's very painful in practice, involve a lot of human intervention and consume a lot of resources. Let me give you one example. How do we find first feasible point for O3 at lambda equals to 19? This island is from bootstrap O3 vector scalar. Bootstrap O3 all the correlator involves vector scalar and range 2 tensor. This is delta phi, this axis is delta s, and delta t is this one. So when we start doing this computation, we know the green box from Monte Carlo simulation. Now that is the more precise result on Monte Carlo simulation, but when we do this computation, the green box is the most accurate result we know. From here, you might say, okay, it looks like it's not too hard to hit the island if we scatter some points in the green box. But let's look at the delta t axis. So what is the probability to hit the island if you only know delta t is around 1.21? So you can say the probability is pretty small. Actually, it's very, very small. In order to find the first feasible point, we have to use some small tricks, and those tricks sometimes is working, sometimes not working. So my point is that in practice, it's very, very painful. Next point is that what happens if our parameter space is not 3D, instead it's 6D or 5D? Then in that case, even if lambda is small, this strategy still don't work, because even lambda is small, it's still very difficult to detect a 6-dimensional space. And the last point is that Bootstrap is also about exploring unknowns. But this strategy requires us to know at least something. So if there is unknown, if there is an island corresponding to an unknown CFT, I want to be able to find it. Actually, you might rightfully ask, since we can only test a finite number of points, is it possible that some super tiny small island in somewhere in this white region? Let's say if the island size is in 10 to minus 30, then we might miss it. So how can we claim the white region is completely excluded? So if you asked me this question in the past, I cannot 100% confident to answer it. So now I want to show you a list of problems that I and my collaborators has spent some painful hours on. And in the past, we pushed those to some limit, but we can never completely do it. And those problems are interesting and have implications for condensed matter physics. One is that yesterday, David Poland told us how to bootstrap all three correlators involve vector, scalar, and tensor. We might want to add one more operator in the system, the range 4 tensor. So the reason is that if you bootstrap this system, then you can have access to the OP coefficient lambda T4, T4, T4. And you can use this OPE to do conformal perturbation theory to know how O3 flow to cubic point. And that will tell you the correction on the range 2 tensor in the cubic model. So if you want to do this system, the parameter space consists of 4 deltas and 9 OPEs. If you use the cutting surface algorithm to do OPE scan, so this 9 OPEs can be handled efficiently, but still you have a 4-dimensional space, and it's actually very difficult to detect the 4-dimensional space. So for this problem, I can find a feasible point at lambda equals to 11, and from that computation, I can figure out roughly lambda T4, T4, T4 is around 14, and from there we can get some estimation of the conformal perturbation theory. But the problem is that I don't know what is the error bar of that OPE. I even don't have a rough estimation for the error bar because I cannot detect the whole space. And also, I cannot do it at lambda 19. I cannot find a feasible point. So this is one example that suffers from the dilemma. It's too precise and the constraint is too strong, so we cannot find the island. And also, even the dimension of the parameter space is small, say in Ising model. Sometimes the dilemma can still happen. Let's say in 2D, we have an island for Ising model by considering correlators involved sigma and epsilon. If we want to follow that island to fraction dimension, quickly that island disappear. Either disappear or get very small. We don't know because if you try to use it, it's very hard to find the island. Same thing for 3D Super-Ising model if you want to mix sigma and sigma prime. Therefore, we need something new in order to handle problems like this. And especially for more and more complicated CFT, we expect the parameter space would become larger and larger. So this is a generic issue. So we want something new. Our proposal is an alternative approach, the Navigator approach. Before talking about the detail, I want to show you roughly how it looks like. Let's still take Ising model as an example. So this is horizontal is delta epsilon and vertical is delta horizontal is delta sigma and vertical is delta epsilon. imagine we do feasibility test for a few points and we find they are all excluded. So in the past, what we can do is that we just have to test more points randomly in this region. But now, with our approach, we can do something better. Actually, the island is here. So after each test, after we find each infeasible point, there is a navigator to tell us which direction we should go in order to get closer to the island. And at this point, so we follow the navigator to this point, and then there is not the navigator to tell us which direction we should go to get closer to the island. So in later step, I represent the final point by the black cross. And as you can see, after some steps, they all reached the island at the step near 40. Around the 40, they all reached the island. So you can say with this approach, we can start the point outside the island, and they will correctly see through the infeasible sea and reach the island. So next, I want to show you how to make this work.
Ming, can I ask you a question?
Yes.
In practice, is it enough just to start with one point outside of the island, and then you're confident that you will end up in the island? Or in practice, you will throw 10 or 20 points, and then if they all converge in the same place, then you say, well, I trust it. That,
thanks. So in practice, you can start with just one point. The issue is that so besides this island, you know there is a continent on the right hand side. So sometimes you might hit the continent, not the feasible region. So you might want to do a few more rounds starting from different points. Therefore, you might, let's say, if there are 3 or more islands, you might be able to land at different places. But of course, if you can, you can just do one round. Actually, it's an advantage for this approach. You can only do one computation and to reach the island. You don't need to do many different computations.
Sorry, so I guess a way of reformulating the question is, I mean, I guess there could be different basins of attraction, and then once you run into the same problem, that you might need to fine tune initial conditions to find some of these basins of attraction. So you're saying that here you go to the island and sometimes you go to the continent, but couldn't there be some other smaller island somewhere that to reach you would have to fine tune your initial starting point?
Yeah, I will come back to this question later. I promise I will come to this question later. So to make this work, one ingredient we need is that we need to define a navigator function. Let's say X is a point in the parameter space. For Ising model case, X is delta sigma and delta epsilon. We want to define a navigator function such that navigator function nx is negative if x is feasible, and is positive if x is an infeasible point. And we want n to be finite and continuous and well-defined everywhere. If we have a function like this, then we can follow the opposite direction of the gradient to decrease n. So we can start with infeasible point where n is positive, and gradually decrease n to reach the feasible region. So how to define a Navigator function? Let me quickly review the original feasibility problem. So this is the bootstrap equation. Let me take Ising single quadratic case. For mixed case, it's roughly the same, but for simplicity, let me consider the single quadratic case. We want to find a linear function such that alpha acting on the vacuum block is positive, acting on spin zero block is positive for delta larger than delta epsilon, and acting on everything else is positive for delta larger than delta unitary. So this problem depends on two parameters. One is delta sigma, another one is delta epsilon. So let me fix delta sigma and delta epsilon at the red cross here. If you run this problem with SDPB, SDPB can explicitly give you an alpha, and you let this alpha acting on the bootstrap equation. You will say on the left-hand side is summation of positive number, on the right-hand side is 0. Therefore, this cross is excluded. Let me show you how those positive number looks like. Also, the red cross is here. So I fix delta sigma, delta epsilon to be this number. And I make 3 different runs for exactly same points. You can slightly change the parameter in SDPB, or you can hot start this point using checkpoint from another point. So in different run, you get different alpha. Here, I show you the result for 3 different alpha. And if you let alpha acting on vacuum block, you get those number, and alpha acting on everything else, you get some positive number. So if you look at this table, you see different alpha. We have many alpha all satisfy this condition, and between different alphas, the positive number is redistributed slightly differently. For example, if you look at this column in different run, it has different value, and here it increases. Oh, also I normalized alpha dot alpha equals to 1 to comparison. So now a natural question to ask is that, can we move all the positivity to the first term? In other words, can we make this number as large as possible while keeping everything else to be non-negative? So say it in other word, can we maximize the objective equals to alpha dot f00 such that alpha dot alpha is 1 and alpha dot everything else is positive? So represent that by geometrically, that means in this plot, the blue vector are those vectors corresponding to different f. And we want to find a plane such that all the vector is on one side of the plane. This black vector is the normal direction of this plane. We want to maximize the dot product between alpha and f00. That means we want to minimize the angle theta between alpha and f00. So okay. So first, alpha satisfies this positivity requirement always exists. Let's go back to our original problem. If you remove this requirement, if you don't require alpha dot f00 is positive, then alpha always exists. If you test this, you will see the whole region everywhere is excluded because you can find an alpha. So alpha always exists to satisfy those conditions. And among all the alpha satisfies the positivity condition, we want to find alpha such that minimizes the angle between alpha and f00. So if the angle is smaller than 90 degrees, of course, our original feasibility problem is infeasible. So the spectrum is excluded. On the other hand, if alpha dot f is negative, then our original feasibility test problem is not excluded. So if we can do problem like this, we have a unique alpha, and we can use the objective function as the navigator function. Unfortunately, this normalization condition alpha dot alpha equals to 1 cannot be translated to standard SDP problem, semi-definite program problem. I think this is still doable, but we have to modify standard semi-definite problem. But actually, it's much easier if we just normalize alpha against some other vectors. For example, we can normalize alpha against the average of the blue vectors. So actually, we have different choices for the normalization vector. And it's a bit technical. Let me postpone the discussion of the normalization vector in a few slides. So for now, just trust me, we can choose some good normalization vector. And this problem is well defined everywhere in the parameter space. And the objective is finite and continuous and smooth everywhere. So our navigator function is the objective as a function depends on the parameter. Let me show you how this function looks like. So here I show you the navigator function for Ising 3 correlated system. And we assume there is the gap 3 in both spin 0, both Z2 even and Z2 odd channel. The left plot, I show you the navigator surface. This axis is delta epsilon. So this axis is delta sigma. This axis is delta epsilon, and the vertical axis is the value from the navigator function. And yellow surface is from lambda equals to 11. Blue surface is from lambda equals to 19. So here, there is a region that the navigator function is negative. That's corresponding to the island. So this on the right hand, this plot is a contour plot for lambda equals to 11 navigator surface. So if you recall from the first paper of Ising mixed correlated bootstrap, there is the island, and on the right hand side we have the continent. There is a large feasible region here, and you will need a lambda at least bigger than 11 in order to find the island. Otherwise, the island is connected to the continent. So here we can understand why. As you can see, island is here, and the continent is around this region. And between them, the navigator surface is above 0. But if you decrease lambda, this surface move. So if you increase lambda, the surface is lifted. And if lambda is too small, then between them the surface is below 0. That's why you don't see in the island. And also from here, we can answer the question, is it possible to ask some super tiny small island in the white region? The answer is no, because as you can see, we have some smooth surface, and it's impossible for this surface to be negative.
But how do you know that your surface, how do you know that I mean, admittedly it's nitpicking, but how do you know that your surface doesn't have a very large spike towards 0 in between the points that you've checked?
Okay. Thanks. Yeah. How can I be absolutely sure that is not the case? Actually, we can later I will tell you. Actually, we can also compute the gradient of the surface, and from there we roughly can estimate if you slightly change the parameter, how much the navigator function should change. Therefore, we can be very confident you will not see a very sharp pike in this surface. Okay. So last thing I want to show you is that as you see here, if you increase lambda, the surface is lifted. So therefore the negative region is smaller, so the island gets smaller. Now I can ask a following question: which point is the most difficult to be excluded? In other words, which point is the most probable point? So this white region corresponding to the island, this point near the tip of the island have a navigator value minus 0.001. On the north hand, the point with the most negative navigator value is the point at this black cross. It have a navigator value minus 0.01. Therefore, when you increase lambda, this point can be easily excluded. But this point, the black cross, is much harder to be excluded. Actually, we know the most precise point for Ising model is the green cross. Therefore, if I only know the island for lambda equals to 19, if I need to bet on the most probable points, I should bet on this black cross instead of bet on the geometric center of the island. And you can see the black cross is much closer to the green cross. So this could give us an estimation for the CFT. Once we have this navigator surface, then we can use we can follow the opposite direction of the gradient to decrease it. The typical path looks like this. So first, you try to move to the shallow valley and working along the valley to reach the island. Specifically, what we actually use is not gradient descent. Instead, we use an algorithm called BFGS, and I will talk about that in detail later. So let's go back to this. Let me show you again how this works. You can see all the paths are first try to work to the shallow valley, and this shallow valley is roughly coincide with the single correlated bond, and then they try to working along the valley to reach the island. and after a while, they reach the point that have most negative value. Once we have this navigator surface, another thing we can do is that one advantage of conform bootstrap is that we can find a solid error bar. Yesterday, David Poland told us how to do O3, how to find the upper bound on O3 range for tensor. And there is a discussion how can we be confident that the value we found is really the upper bound. And since we only test some finite points, how can we be confident about that? So once you have the navigator surface, you can handle this problem much more efficiently. Let me take Ising model as an example. Let's say we can try to maximize delta sigma over delta sigma delta epsilon parameter space while keeping the navigator function to be negative. So this is a typical path. You can see it quickly reaches the very tip of the island. And after 17 steps, the precision is around 10 to minus 30. So it's super precise and very efficient. Therefore, this navigator approach can actually replace the traditional method. If we want to, so first we can use the most probable points as an estimation for the CFT, and also we can maximize or minimize the parameter to find the solid error bar. Okay, so we missed a few technical points. One is that how to choose a good normalization vector. Another one, as I mentioned before, we can effectively compute the gradient of the navigator function, and how to actually do optimization problem like this. So those are quite technical. Before I go to those things, is there any questions?
Yeah, maybe I would like to ask. So the algorithm you showed, it's basically the same that you would do to put upper bounds on OP coefficients, right? So in some sense, so you're using the upper bound of the OP coefficient as this navigator, or is it a correct intuition?
Okay, thanks for the question. So actually, if I know correctly, actually that is the first idea for the navigator function. I think people tried that back to 2014. But the problem is that if you use the bound of OP coefficient as a navigator function, that only well defined inside the island. It's not well defined outside the island. If you actually use SDPP to do that, you will see the objective go to infinity when you move outside the island. So therefore, you cannot do that.
Okay, thanks.
Ning, there was a question on Slack. So Wei Li is asking, what about starting in the island for small lambda and then applying the navigator to get an island for large lambda? Do you want to comment on this now or maybe later?
So start from small lambda and find the island for larger lambda.
Yeah, it's the first question on the chat. I don't know if you want to take a look.
I'm not sure I understand the question correctly. But
well, the question is, can you use this navigator to find islands by increasing lambda gradually?
Oh, okay. So so first, why we wanted to do that? If we have the Navigator function, we can directly start at a large number. But of course, you can still do that. And I guess perhaps one thing you can do is that you can find the most probable points at different lambda and try to extrapolate that to lambda infinity. That might give you a better estimation for the CFT. Okay, if there is no more questions, I want to discuss those technical details. So first, how to choose a good normalization vector. The naive choice doesn't work. Let's say if you want to normalize alpha against the energy momentum tensor, which is delta equals to space-time dimension and L equals to 2. If we want to normalize in this way, it doesn't work. You will say the objective will go to plus infinity in the disallowed region. Why this is the case? Actually, so it's easy to understand it. Imagine imagine the block for the energy momentum tensor is this the fourth vector is this vector. So all the vector form some kind of cone, right? So imagine this vector is on the boundary of the cone. So you can move this alpha a bit such that alpha is perpendicular to this vector. Therefore, if that is the case, then you can rescale alpha as large as you want, such that alpha dot this vector is still to be 1. Therefore, your objective, since you can rescale the alpha, therefore your objective can be as large as you want. Play same argument. You can say normalize against any vector on the boundary of the cone is not good. But from here, immediately we say we can fix this. Just normalize alpha against the average of those vectors. In that case, you normalize alpha against the vector roughly in the center of the cone. In that case, you cannot rescale alpha arbitrarily large and still keep the normalization condition. So specifically, what does that mean? That means we can normalize alpha against the average of those vectors. So we can integrate those vectors and sum them up and use this as a normalization vector. If we do this, then alpha has to be finite. Actually, this automatically guarantee those positivity condition is positive at the same time is finite. Because if any of those number diverges, then this normalization condition cannot hold, because there will be infinity somewhere here. In practice, of course, we can do it much more in a much more easy way. We just normalize alpha against a few vectors to be 1. We just sum a few vectors and then normalize alpha against those vectors. That would be enough. Because here you can say my argument why this doesn't work is because I can find an alpha perpendicular to this vector. But if I normalize alpha against the sum of 3 vectors, and that is enough to ensure alpha is finite. Because if alpha is infinite, I cannot find an alpha to be perpendicular to 3 different vectors if those vectors are linearly independent. So since in practice, alpha, we translate alpha in finite component, so we can just sum up a few blocks, and that's enough. Actually, we have a different choice for the normalization vector, and this goes back to the question: can we use bounding OP coefficient as a navigator function? So actually, you can, but you have to do it more carefully. So as I mentioned before, if you do that naively, let's say if you want to bound the central charge, then when you're moving outside the island, the objective will go to infinite. So how can we fix that? We can fix that by adding a term in our bootstrap equation. So let's again take a single quadratic case as an example. We know there is a solution which always exists. That is the generalized free field solution. Therefore, if you let's say you fix delta sigma and delta epsilon at the red cross, this point is excluded. But if you add a term here on the GFF line, if you add this term, then of course you can find a solution because GFF always exists. Then you can try to minimize this coefficient and use this coefficient as the navigator function. So minimize this coefficient corresponding to normalize alpha in this way. And this requires some knowledge about how to bound the OP coefficient. And I think this is not mentioned before in the lectures, but Martin promised to discuss it in his tutorial, so I will skip this part. So the punchline is that if you normalize vector like this, is corresponding to minimize this coefficient, and you can use this coefficient as your navigator function. Now the technical detail is that how do we evaluate the gradient effectively? Actually, we have a simple formula that you can get the gradient immediately without any iteration process. To really explain this formula, I have to go to semi-definite program formulation, and we don't have time for this talk. But let me just telling you the dB, dc, d capital B variable in this formula corresponding to change of the bootstrap condition due to the change of the parameter. And x and y in this formula corresponding to the solution to the semi-definite program. Actually, y is corresponding to the functional alpha. So in practice, what we do is that we use SDPP to run the navigator problem, to run this problem. And when we maximize the objective, we get an optimal solution to the semi-definite program. That is the checkpoint of SDPP. And then we can vary the bootstrap condition by finite difference method. Or if you want, you can also try to compute the exact variation of the conform block due to the change of parameter. Actually, I think this motivates, for the analytic people, I think this motivates the study of the conform block again, try to study the change of the block, the derivative also block respect to external parameters such as the dimension or scaling dimension of the external operator or change of the space-time dimension. So you give this optimal solution and the variation of the bootstrap condition to a new tool we developed, but it will be released in the SDPP toolbox. And then this tool implements the gradient formula and directly give you the gradient. But I want to give you some flavor why such gradient formula should exist. Basically, when you have optimal solution, your solution under the bootstrap condition has to obey some constraining equations. Therefore, in that constraining equation, if you vary the bootstrap condition in first order, then the solution should also vary accordingly. Therefore, from there, you will be able to find the change of the objective due to the variation of the bootstrap condition. And also, if we understand the variation of, if we understand how the objective should change, if we slightly vary the bootstrap condition, we can also answer another question that raised in yesterday's discussion. And the discussion is that we get this island, but there's some approximation we used. We approximated the conformal block. So then how solid is this bound? The answer is that the solid error bar is very solid. The reason is that you can estimate if you how the error bar in your approximation of the conformal block affect the navigator function, how much the navigator value would change if you make a better approximation in the block. And from there, you can understand how this bound should change if you use a better, if you use a different approximation. Roughly in this case, I estimated this bound should change in something like 10 to minus 5. Therefore, the error of the solid error bar can be quantitatively controlled. Okay, this is the gradient formula. Another thing I haven't mentioned is the how do we actually do the optimization? So if we can evaluate cheaply for the gradient, let's assume at step k, I'm at xk and the gradient is gk. And the gradient descent tell me I should move in opposite direction to go to xk plus 1. And at xk plus 1, I find the gradient is gk plus 1. If you have those information, immediately you realize you actually also understand a little bit about the Hessian. The Hessian is the derivative of the gradient. So if you know the gradient at here and at here, if this 2 point is close enough, then of course you can figure out some information about the Hessian. Specifically, let's define y equals to the difference of the gradient, s equals to the difference of the coordinate. Then the Hessian is b. Then the Hessian dot s should equals to y. BFGS formula tells you what you can BFGS tells you that what you can do is that you can still do a gradient descent, but at the same time, you can try to approximate the Hessian. So basically, if we assume the Hessian at step k is bk, then you should use this formula to update the Hessian at the step k+1. And as you move towards the optimal points, the distance between steps get smaller and smaller. Therefore, your approximation for Hessian become better and better. And if you have a good Hessian, then you can much more effectively to go to the optimal points. So at k+1 step, we can approximate the Navigator surface using the gradient and the approximated Hessian. Then now we have two choices. Either we can minimize the Navigator function in this approximated surface. This is the standard BFGS application. Or we can try to maximize delta sigma while keeping the approximated Navigator surface to be negative. So this choice is the one we used to do this optimization problem. And the standard choice is the one we used to find the most probable points. So let me show you the problem for maximized delta sigma. If we look at the difference between xi is the coordinate for those points at different steps. If you plot xi minus last x versus a step, you see it decreases very fast. So this is quadratic convergence. And that's it. So the outlook is there are many things we can do. First, those problems I mentioned before, now we can do it. We can use this to scan many parameter space. And I tried like six-dimensional space. There is no problem. And also just for just brainstorm a little bit for this workshop. I think in later sessions there is a discussion for non-unitary CFT. Just imagine in the non-unitary CFT, if we know there is a few blocks which have negative OP square coefficient. Perhaps we can do it. We just sum this term together with the vacuum block, and we just scan the OP coefficient and this operator. And you can also imagine in the past we usually try to say if some operator does not exist, then it's inconsistent. Now we can try to say if some operator exists in some region, it's inconsistent. We just sum that operator together with the vacuum block, and we try to scan that operator. So there are many things we can do. Thank you.
Okay, well, thanks, Ning. Are there any questions?
Ning, may I ask you a question? Did I understand correctly that you have two candidates for the Navigator function? Can you briefly compare them? just how well they work in comparison? What is it better to choose one against the other?
I think both works well. And in those plot, we used the second one. We used the GFF navigator because that gave us a unique value, and it has more physical meaning. If you do the sigma navigator, then that depends on how you choose those finite set of points. So this for the sigma navigator, you have many different choices for the normalization vector. On the other hand, if you want to say the navigator service near the GFF, if you want to plot the navigator service near the GFF or below the GFF line, then you have to use the sigma navigator, because the GFF navigator is not well defined on the GFF line or below.
I see. Sorry, but can you say you can go below the GFF with the sigma navigator?
Yeah, sigma navigator is well defined everywhere. So for GFF navigator, below GFF, you don't have this term, right? Because you already have this term.
So, okay, let me ask you a little bit later. I'm confused about one point about the GFF, but yeah, thank you.
You're welcome.
Can I ask a question?
Sure.
Yeah, so the navigator function seems to be like, it seems to have like very good property because you don't get a huge number of attractive basins, right? But do you have any argument to understand why it is the case?
So could you repeat? You don't have
a lot of basins, like if you want to minimize the navigator function, but then you're trapped with like at some positive region, like do you have some argument why this doesn't happen?
Why you don't trapped in some region?
Yeah, I guess the question is why you do not have local minima apart from one interesting one.
Oh, okay. Actually, I don't know. Maybe for more complicated setup, maybe you could have some local minimum. And I guess if that is the case, you have to do multiple run. So perhaps you have to do several run in order to go to the true island. I think in general it's possible to have a local minimum.
If you have a theory with more than one fixed point, presumably there will be more than one minima.
Yes.
Will you be attracted to one island preferentially relative to another, or would they be all equally valid?
So the algorithm we use, the BFGS algorithm, works locally. So in that case, if your point is close to one island, you might reach that island. Then another point close to another island might reach a different island.
Oh, okay, right, okay. I'll be back in a minute. Yeah. But would the sort of dividing line between the two islands be roughly in the middle? Would be a bifurcation?
Yes, actually, we already see one example, which is so you see you have a continent here and an island here. If you look at the navigator service, there will be some set point between them. Yes.
Further questions?
Yeah, can I ask a question? So in linear programming, these conditions that you were mentioning, the gradient conditions, you can write down second order optimality conditions known as the Karun-Kushter, well, the KKT conditions, which then allow you to move along the boundary. But there it's crucial to also have that the fact that you have not only an optimal functional, but that you also look at the extremal solution that goes along with it. And if you combine the two, then you get these stronger conditions that allow you to move along optimality. So is there an analogous, are there an analogous set of conditions in the semi-definite program case?
So are you saying that there is no way to move along the boundary?
Not just at the boundary. I mean, whenever you have an optimal solution, there is a way of smoothly deforming it to any other optimal solution.
Yes, actually, sure. So actually, one thing we are trying to do is that we can further improve this algorithm. So instead of doing step by step, maybe at some intermediate step inside SDPB, we can compute the variation also respect to the change of the bootstrap condition. So we can change the direction inside this DPB, and it could be one run gradually move towards the optimal point. Is this your question?
Yes. I mean, basically, the difficulty in generalizing this story, I think, is simply that in your case, usually you also want to be changing the external dimensions. I mean, you're imposing a gap that also depends on the external dimension because you want epsilon to appear DOP of sigma. But otherwise, anyway, it would be interesting to see how to generalize this story to this case. The other question is, for instance,
Miguel, could you repeat your previous point?
I'm saying that
to which case?
So I'm saying that these conditions that I mentioned, they can be applied easily in the single correlator case because you don't have this problem that you have coupled things, that an operator appearing in DOP in one channel also appears as an external operator in another channel. I guess if we had some efficient tools for computing blocks at any value of external dimension, that I think probably could implement this gradient flow, but I don't know how to formulate it directly in this semi-definite language, only as a linear program involving extra continuous parameters. So I was wondering, maybe there must be a more efficient way to do it. So this was my question.
I think I don't completely understand the thing you mentioned, but for single correlator case, we can do something very efficient. We can map out the single correlator bond super efficient, and we can change the slope of the bond as well as the second order derivative of the bond. We can do those things very efficiently.
Yes, yeah.
I'm sorry, maybe I understood a bit better Miguel's point, but I think there is a very good analogy. So I think, Miguel, if I understood correctly, you said that for you it was important to have access both to the solution and to the optimal functional. And in our SDP gradient formula, indeed, it's important to have this formula that we have a primal dual solution. In fact, X is the solution and Y is the functional at optimality, and they both enter into the gradient formula. And to using this formula, I think we can do many things. In particular, we could implement this gradient flow that not gradient flow, the going along the boundary is very easy because you just use this gradient to make a small step, then you correct. In fact, Ning has more plots which do precisely that. Like, okay, well, for example, he showed these plots which optimize delta sigma. And when you optimize delta sigma inside the island, you can do it in different ways. You may want to go along the boundary of the island, and you may want to stay close to the boundary of the island, or you may want to like cut through the island. You can do different things. In this particular plot, he showed that his optimization algorithm cuts through the island, but there are also other algorithms which like closely follow the boundary of the island, and they also, I mean, they work a bit slower because they get more information along the way.
I think you can also you can just also flow smoothly inside the island, right? Because at any point inside the island, you are optimizing some objective function. So you will have a solution, an optimal solution at any point. So
you can do many
any
things.
path that you want, you can move smoothly.
You can,
Miguel, I think now I understand your question. So basically, change of the so basically evaluate the block is the iteration process. You do SDPB is not the iteration process. I think eventually we can make both integrated into one iteration process. That you do some step in SDPB, then you determine how your block should change in order to reach minimum point, and you determine how the solution should change. So in each step, maybe you can change your solution at the same time also change your block in order to reach the some point you want. That would be one smooth run to some point. Yeah, we are actually working on that.
I see. I guess what I'm saying is that I would know how to do these flows in a multiple correlator setup simply by rewriting it as a linear program, where basically on top of the scaling dimensions, which are a continuous variable, you would have the other continuous directions. There will be like the directions in OPE space, right? So this adds some extra continuous variables, and then you could do the flows like that. I don't think that would be a problem, but it's probably not the most efficient way, since in your case you have these matrices that automatically capture the properties at all delta. There must be a faster, more efficient way to do it. So this was more the point of my question.
Okay, thanks.
I think if the question is, can you do the flow directly in SDPB? Yeah, I think we can do the flow directly in semi-definite setup.
Yeah, but using the special properties that you have these polynomial representations of the blocks.
No, it's not a property of polynomial representation. Just the question is there a way to deform a solution of semi-definite program? You said that you know a way to deform a solution of linear program.
No,
there is also a way to deform a solution of any semi-definite program. So you don't have to rewrite semi-definite program as a linear program if you want to deform a solution. You can do it directly in semi-definite setup. Further questions?
Practice that you need to find optimal solutions rather than just primal or dual.
I'm sorry, Alex, there was a beginning of your question got lost. Can you?
So is it a problem in practice you need to find optimal solutions rather than just primal or dual? I mean, in terms of performance, like these things take quite a lot longer, no?
Yes, it will be a little bit longer, but not that longer. So for example, if you run this point to find the optimal solution, I think it's run 3 times longer than feasibility problem. But still you just need a few runs to go to the boundary, and with some trick you can actually effectively hot start those runs. So when you run a certain point, it won't be that much of time. So overall, you still gain a lot.
Okay, thanks.
I have a question. So since you have the solution, since you have the gradient of the solution, can you use the gradient of the solution to like shift your hot starting initial condition to like let it converge even faster?
I think this is essentially what Miguel mentioned. So
Yeah.
basically, if you have this thing in the intermediate step, you can sort of hot start and change the bootstrap condition a little bit. Then yeah, you can.
Okay, thanks.
I think it depends how aggressive you want to be, because you may choose, indeed there are two philosophies. You may say, okay, I know the gradient, let me just make a big step in that direction. And then maybe hot starting is not going to work so well. Or you can try to follow this philosophy, let me just be super careful, I will do like infinitesimal steps and flow in that direction. Then you will have to make more steps. But maybe you will be able to take advantage of hot starting. So it's still, I mean, this tool is very new, and it's still not clear what is the best way to drive this new car. Further questions? Well, I would like to add with the comments. So we started this week kind of, okay, so we had, yeah?
So I would like to do a question which goes a little bit beyond, let's say it's quite general, and probably it is addressed to all of your community, let's say. So until now we've seen like wonderful progresses, technical progresses that allows to restrict this island of a possible bootstrap solution. I was wondering, suppose you do this in, you run this in b-dimensional models, and so we know because of greater symmetry that we have some structure, some multiplicity, some mathematical structure, no, behind the two-dimensional, in two dimension. Can you see this structure? I mean, this in your research, like in these years, can you see this method can point out to some structure also in any dimension, like the existence of null vector, for example, the kind of the multiplicity, some multiplicity, and so on. So it, like there are also some you have some more insights of some hidden structure in any dimensions, like for example, it is an echo for what it happened in two dimensions, or not, or we were going to see during this program. I don't know if I was clear.
So the question is, when you say dimension, you mean space-time dimension, right?
Yeah, so I repeat, like, for example, in 2D, I mean, you know that because of you have a Virasor symmetry, you have a given multiplicity of fields. You have, if you have a field of dimension delta, you have to have at least two fields of dimension delta plus 2. I mean, like, you know, you have the Virasor, yes, or the Virasor towers, and because, yes, you have this big symmetry, and that has also a lot of mathematical structure that allows analytic solution.
No, but if you are serious, you would like to do 2D bootstrap with Virasoro blocks, it would be a bit stupid to do.
Sure,
I mean,
sure.
sometimes we do 2D bootstrap with SL2C blocks just as an illustration, but if you are a serious professional, then you have to do 2D bootstrap with Virasoro blocks, and then all of this structure will be automatically built in.
I totally agree, but my question is that if this approach can see some structure which is true in dimensions which are different from 2.
Oh, okay. I think I understand your question. Yeah. Actually, I'm very interested in that question. So basically, your question is that if I understand correctly, perhaps your question is that can we use this approach to do two-pass epsilon Ising model to understand how two-pass epsilon works? When you start to increase space-time dimension, what happens?
For instance, yes.
I think this approach will be essential for this problem. And
No, but Ning, the question, sorry if I correct you, but the question was not in this navigator approach, in general. Well, can you answer in general? Do we see any interesting structure in the spectrum of conformal field theories, say in 3 dimensions or in 2.5 dimensions, to your knowledge? How can you answer this question? Is there anything interesting going on? We know like hundreds of operators of 3-dimensional Ising model. Do you see there any Virasoro multiplets or anything like that?
Okay, very good question. Yeah, I mean, I'm very interested in that. So, in the past, it's hard to do mixed-polarity inflection dimension. So in the past, it's hard, but now I think we can do it. Another thing is that I just you can ask how. So in 2 dimension we have a lot of structure. We say those null state play an important role in 2-dimensional CFT, and we have this argument. We must have some null state in order for the CFT to be in a unitary minimum model. So I guess one interesting question is what happens to this structure, those structures, when we slightly move above 2 dimension, and what happens of those things in 3D? Yeah, it's a very interesting question. Let me just say, now with our approach, we can do a lot about that. So for example, if you carefully check the single correlate bound using our method, I mentioned you can do slope and second order derivative precisely. What you will see is that you will see some discontinuity in the single correlate bound. Not exactly on the kink, because the kink is a human perception. But if you check the bound carefully, you see some discontinuity on the bound. And those discontinuity corresponding to some underlying spectrum change. In fact, one discontinuity corresponding to the level 2 null state in 2D Ising model. Now, I guess you can follow that to spectrum dimension and check how those spectrum changes, spectrum decoupling, spectrum recombination happens in spectrum dimension, and how this behave in 3 dimension. Yeah.
Perhaps another answer to this general question is that, I mean, we do observe the idea of like Reggie trajectories. So like the idea that like if you look at very large spin, then even in strongly interacting CFTs, you see operators which are kind of like roughly integer spacing above that spin. I mean, this is something which we also understand analytically, but like nonetheless, you do see it numerically by looking at these kind of 100 operators you can read off in the numerical bootstrap. And so I guess if we hadn't known this analytically, then this is something maybe we could have discovered from the numerical results. And then this is something which is general, beyond 2 dimensions. So I don't know.
So maybe we can organize some discussion about that in the next in the days to come, because these are interesting issues actually.
Yeah, I think about Reggie trajectories. There's going to be some discussion in week 4, but we could have some early discussion. If yeah, it would be a bit premature, but yeah.
In any case, thanks. Huh?
But there is no Virasoro. I'm sorry to disappoint you.
Not,
or at least we have not seen it. We have not seen it, nor in 3 dimensions, nor in 2.5 dimensions. Well, there's going to be maybe Andre Capelli. I don't know if he's here, but maybe he's going to say something about this in his tomorrow's talk about spectrum of Ising in non-integer dimensions. But in principle, the current prejudice is that Virasoro is lost when you go from 2 to 2.2 plus epsilon. And then, but then there is some other structure like Regge trajectories which emerges, which however is not as, is more flexible because Regge trajectories are some trajectories, well, they're deformable to some extent and they talk to each other and so on. It's not symmetry, it's more dynamics. Yeah. But okay, I just wanted to say that, okay, we had like 3 talks about numerical bootstrap this week. We had the introductory lectures by Alessandro Vicky. We had a seminar by David Polland, which showed kind of what the state of the art is, like what you can do. And we had the seminar today from Ning Su about kind of, which is really cutting edge and forward looking. And, you know, I understand it may be this seminar today was a bit technical for the statistical physics part of the audience, but I think at least you can be sure that you've seen like what the state of the art is. So there's nothing that we are hiding. We have all our...
And we are impressed.
All our aces are on the table. We have little up our sleeve to... as far as numerical things are concerned, there's going to be some analytical things in later weeks. But okay, so these are the tools that at our disposal, at least for unitary theories. And okay, we have to come up with good things to attack using these tools. And for non-unitary theories, there are going to be tools discussed later. And yeah, so there is going to be some discussion on Slack about, so Ning mentioned some ideas that he has about how to use this perhaps even for non-unitary theories. I see some people posting discussions on Slack, so there's going to be discussion there. Okay, well, with this, I would like to thank Ning for this very nice talk. And
I also have a question.
Sure, Kai, go ahead. There's a
first of all, I would like to thank Ning for this very clear talk, which was not too technical, I think. I have a question on the structure. So if you bootstrap the O2 model, there are 2 fixed points in perturbative RG, the O2 symmetric and where you are, I mean, the interaction is just phi I to the 4. So, I mean, which is an Ising model, uniaxial, they call it. So do you see this in the bootstrap?
The question is, do we say O2 and Ising model? Yeah, I guess we say that. But I'm not sure I understand your question clearly.
The other Ising model, the 2 decoupled Isings, you mean, Kai, can you explain what is this other theory? Is it?
When you do standard perturbative analysis.
But does it have
n vector model?
Does it have O2 symmetry, this other model?
So if you have a 2-dimensional, n-dimensional vector, there are 2 fixed points we know of, which is a uniaxial fixed point, which looks like an Ising model, where the ON symmetry or O2 symmetry is broken, and then the O2 symmetric fixed point. But if you say you have 2 components for your vector, you have both fixed points. So you should somehow see 2 islands in O2.
I think for O2, you only have 1 fixed point with full O2 symmetry. But perhaps you can ask a similar question. Instead of O2, maybe you can ask a similar question in O3 case. In O3 case, you have this O3 fixed point and another fixed point which bridges O3 symmetry to cubic symmetry. I guess perhaps with cubic symmetry, you will see 2 islands, 1 corresponding to O3, 1 corresponding to cubic model. But that is much more difficult to do. Right now, we don't see 2 islands. For O2, I think there is no other islands than O2 and
No,
Ising.
but can I make a comment about terminology? Because Kai, when we say O2 model, we don't count fields. When we say O2 or 3, it means that we are studying CFTs which have O2 global symmetry. This other fixed point that you mentioned, it exists, of course, and it is a CFT, but it does not have O2 global symmetry because, as you said, O2 symmetry is broken. So that fixed point will not be seen in any bootstrap analysis which inputs O2 global symmetry from the start. To see that fixed point, you have to do another bootstrap analysis where you will input from the start the symmetry that the fixed point will have. You know, and in that case that you said, it's going to be just Z2 because you break it to Ising. So you do bootstrap analysis global symmetry by global symmetry, where global symmetry is the final symmetry of the fixed point.
Has any numerical
Suppose
bootstrap
I
seen
don't
two
know.
islands?
Can the bootstrap tell me which possibilities there are?
By what do you mean you don't know? You have a finite list of groups. You just go through the list of groups one by one. For each group, you set up its own bootstrap analysis. You study systematically all the islands, and then you keep going. That's the philosophy.
Okay.
But has there been a case where there are two islands in the numerical bootstrap which are kind of competing with each other?
For now, no.
Well, I mean, of course there are. I mean, like when you have cases with more supersymmetry, you have in a sense infinite islands, because like I mean, you have theories, you have like families of theories which have the same global symmetry, but they are labeled say by the central charge, and you literally have infinite of them, and then you can get a different island for every single value of the central charge. I mean, of course, you know, you also have cases with less supersymmetry, which are conformal manifolds, in which case you would expect to get a different island for every point on the conformal manifold. So yeah, so indeed, there are many cases where you get, you know, billions of islands within the same plot.
But they've yet to be found.
It would be an exaggeration.
No, they already have been found. They already have been found. But these are just cases with more supersymmetry, like such as, you know, maximally supersymmetric in 3D, for instance.
So I guess the answer, the more like the more balanced answer would be that there are some cases, but I wouldn't say that there are many cases.
Sure.
In particular, it would be very interesting to see some cases like that with less supersymmetry and yeah, some of relevance to statistical physics. But I'm not aware. Maybe Ning, would you like to comment, because we are monopolizing? It's your seminar after all.
Without supersymmetry, as far as I know, probably no such case. But I hope perhaps one can find this case in cubic symmetry. So there should be an island corresponding to cubic model and another island corresponding to O3. But I'm not sure with current computational power we can do that.
Sorry, I'm a little bit confused about that, because like if one theory has more symmetry than the other, then if you're imposing the bigger symmetry, you shouldn't see two islands, you just see one, right? I mean, assuming you look at a wide enough.
So what I'm trying to say is, in the cubic symmetry, you impose the subgroup symmetry.
No, I'm saying if you impose like O3 symmetry, and if you look at enough correlators, it's impossible that you could see this cubic symmetry, because that's a smaller group.
No, but you start with cubic symmetry, then you can find O3 symmetry.
Yeah, that's what I'm saying.
The smaller group, you can see the bigger group, but.
Well, one can also imagine other theories, maybe like in 2 dimensions, where we have, or in close to 2 dimensions, where we have non-trivial CFTs, which have both critical and anticritical fixed points, and they have the same symmetry. So we should see in principle 2 islands, if we can isolate both of them.
I guess next week.
Yeah, so maybe Shai is going to show us something.
Well, not islands, but 2 kings.
Yeah. So, but indeed there is so there is an interesting problem out there that Hugh, that you are because in some cases, for example, there are in perturbation theory, it's known that if you do perturbation theory in multi-scalar field theories around epsilon dimensions, that, for example, it's known that in perturbation theory there is only a single fixed point with certain properties which is stable. So there may be many fixed points, but there is a single one which is stable. And stability is a particular condition that we can impose on the bootstrap in terms of the number of relevant operators. And so, for example, this kills off 3 critical points because they have more than one irrelevant operator. And so it would be interesting to find some symmetry where, for example, in 3 dimensions, there would be several fixed points having exactly the same number of relevant operators, relevant singlet operators. That would be really a very interesting deviation from what one expects in perturbation theory. And it would be, for example, only one of those fixed points would be then connectable to 4D via the epsilon expansion, while the other one would have to come from somewhere in between. So it would be very interesting to find such a case, but I think it's not yet been seen in the bootstrap. Although there's some conjectures about that from Andy Sturgeon that he's going to talk about in week 3, I guess, but it's not 100% clear situation.
Okay, so if I rephrase what you just said, so if I take again the example of 2 components and I put the bound for the epsilon prime below the dimension of the instability of a cubic fixed point, and I don't impose the cubic symmetry, I only impose the Z2 symmetry, then I should see 2 eigenvectors.
In practice, usually you don't. And usually that is a huge region connected to fixed point. Because in order to say an island, usually you have to put a condition that is enough to separate this CFT from everything else. So it's a bit tricky.
So the answer to Kai's question would then be that with the conditions that he mentioned, there will be some allowed region which will include both the cubic fixed point and the Ising. But unless you make further assumptions, that allowed region may not separate into 2 islands, it may be connected.
But I mean, this navigator function would have 2 minima.
Oh, that would be interesting. Actually, one thing I can tell you is that if you use this sigma navigator, sorry, what I want to say now might be a bit premature, but I guess you will see the navigator value close to 0 on the single collector bond, but also close to 0 near the GFF. So perhaps what you said might be correct.
The cubic anisotropic fixed point and the O2 fixed point.
Yeah, I guess what you said might be possible. Although we have a large region connected to fixed point, but maybe you say 2 minimum inside it. I never tried, but it's an interesting idea. I guess I should try that for cubic versus O3.
Yeah, just take 2 components. It's easier.
2 components. I'm not that sure about it.
But there are 2 fixed points of the RG. I mean, I can also ask. There is a fixed point of the RG which is special and under the realization group flow, even if it's maybe unstable fixed point. How does it show up in your navigator function? Or you have to invent a new navigator function to tell us I'm at a fixed point, even if it's unstable or something.
I'm not sure I understand the question.
I think the question is that, I think if I understand correctly, Kai is having some general questions about the navigator function, and he wants he's wondering if it would be interesting to test those general questions in the O2 model setup. While our feeling is that the O2 model setup is kind of boring because, yeah, we will clarify this question that interests Sky, but we don't expect to learn anything particularly interesting new about the O2 model because we already know a lot about it. And so we would like to test this Navigator function on some models that we haven't studied yet. So that we will in parallel learn something general about the Navigator function and also about some physics.
Okay, and then let's do this on all three. But I also want to know what this Navigator function, I mean, what can it do? Can you tell me that I'm at a fixed point, for instance? Because I mean, there are two different concepts. I mean, the RG is talking about fixed points, which don't have. I mean, there is no notion of unitarity. It's just a fixed point, and this is the point we are interested in. You say, okay, I look at unitarity, and that's my guiding principle. So we have to bring them somehow together, or to see whether there is a hint of one in the other approach. If we want to get more mileage down the road for disordered systems, I mean, that's at least my thinking.
So your question is, can we use this to do non-unitary cases?
Well, before going to non-unitary cases, I think the example I gave is unitary. Well, hopefully. So what? How does a fixed point? Is there any signature of a fixed point in your formalism? Any of them? Navigator function I liked. But you can come up with any of these carving algorithms. Is there something? Okay, let's say it's an indicator function for RG fixed point.
I guess when we do Bootstrap, we already assumed it is at the fixed point. So we cannot.
Isn't it the statement that the Navigator, it's the zeros of the Navigator function in some sense? Once you put enough constraints, then this function will be,
yes.
I forget your convention, it's when it's infeasible, it's positive, right? So it's going to be positive everywhere. And then right at the fixed point, where a CFT actually exists, it will just be zero.
But it has nothing to do with RG though. Like it's not like when it's not at the zero, thus it's related to some other RG thing.
Yeah, no, it has nothing to do with RG because we're always talking about CFTs. But in the space of theories, the good theories are the ones where this function, there will be some function that on the CFT data, you input the CFT data and it will have zeros at the only consistent
yes.
data.
So as you increase the lambda, at the most, so as you increase lambda inside the island, the Navigator value will become larger, but still below zero. I think eventually at infinite lambda, probably it becomes zero, and there is only 1 point corresponding to the island. Yes.
Yeah, actually, I didn't understand, Kai, your question. When you talked about the Navigator function for RG, did you mean the Navigator function that Ning talked about, or did you just think that is there something like this for the problems that you work on?
And then you came up with a lot of interesting measures on this Navigator function I really like. But is there something which tells me that I'm at a fixed point of an RG equation, for instance?
But that's something that is going to tell you that at a fixed point, you want that something to depend on what variable?
I mean, if
there's
only one,
the couplings.
If I do easing, there's just the kink, which is a fixed point of the RG.
But forget about kink. Kink is like it's ice age. Now we talk about islands and stuff. So kink is the thing of the past. So
If you
have the
follow the
island.
RG trajectory, it goes through the disallowed region, and then
I don't think this terminology is allowed. RG trajectory does not. You have an RG trajectory in space of couplings. I don't think you have the right to transpose that RG trajectory into the space of CFT data. That's not an allowed procedure. It's just two different spaces. Of course, you have a space of couplings, and once you reach the fixed point, that fixed point will be somewhere in the space of CFT data. But the RG trajectory itself, it lives in another space. It lives in the space of couplings that CFT does not have the right to talk about. You shouldn't think that your RG trajectory goes somehow through disallowed region and reaches the fixed point. I think that's this language is not theoretically justified.
it would be a projection.
Not even a projection, because, for example, scaling dimensions, they are not, as long as your theory flows, you cannot define scaling dimensions, so you cannot define OPE coefficients, because all of these quantities are scale dependent. They are not really well defined. For example, scaling dimensions say that only certain 2-point functions are non-zero and they scale with a certain power. If you are in the middle of the RG flow, you have all 2-point functions are non-zero and none of them scale with a particular power. So you cannot even say that you have any particular set of scaling dimensions. So how are you going to project this to the space of CFT data?
So you have no analog of Samolotchikov C theorem, for instance.
Yes, there is an analog of Samolotchikov C theorem for RG flows in high dimensions.
Now,
There are some functions that people cooked up. For example, there is something called A function, and there are some gradient flow and so on. But those are different objects. They have nothing to do with the navigator function that Ning discussed today.
You're sure we are drifting off to much more general questions.
Yeah. It's, but these are interesting.
Let me just mention one thing. I think this navigator function is general for semi-definite program. Therefore, let's say if you can formulate some other physics problem outside CFT in terms of semi-definite program, then I guess you can use similar things.
Hmm.
Well, I mean, we have the discussion is a bit freewheeling, but on the other hand, you know, if people want to continue, there is no problem. We should continue. You know, if somebody is fed up, they don't have to stick around. So, so if somebody else has any comments or questions, they should just pick up. No questions. Okay, well, I guess we will then adjourn until 3 p.m. Right, when we will stop. Yeah, thanks, Ning.
Thanks.
You did a great job. Thank you.
Thanks a lot.